In this lecture, we're going to continue our discussion of isomers. Specifically, we're going to talk about isomers of coordination compounds. We will discuss octahedral coordination sphere isomers with monodentate ligands and chelating ligands, and then we'll move on to square planar and tetrahedral coordination spheres. Finally, we'll discuss structural isomers of coordination compounds. Okay, so previously we introduced the definition of isomers. We talked about structural isomers versus stereoisomers, and we defined geometric and optical isomers or enantiomers. So we introduced them with their general definitions, and then we started specifically applying them to coordination compounds. Just as a reminder, there are two main types of isomers. There are constitutional or structural isomers. Molecules have the same formula, but different connectivity. Whereas stereoisomers, we have the same connectivity, same formula, but just different spatial arrangement. So this is an example of a pair of enantiomers, and these are structural or constitutional isomers. So specifically, as it applies to coordination compounds, that's what this summary slide is saying. So far, we have introduced stereoisomers specifically for coordination compounds. So we're going to finish this discussion, and then we will come over here and talk about structural isomers. So just as a reminder, for stereoisomers, we have two different types of stereoisomers. We have geometric isomers and we have enantiomers. So geometric isomers have different spatial arrangements that result in different geometries. So that's the big key with geometric isomers. And enantiomers have the exact same geometry, the exact same connectivity, but they have a different spatial arrangement because they are non-superimposable mirror images. Coordination compounds, already we talked about a few different cases. This was the MA2B4 case, and we classified this as our trans and this as our cis. And we were classifying this relative to the chloroligands. So here the chloroligands are on opposite sides of one another. Here they're on the same side. So this is our trans and our cis geometric isomer. And neither one of these was chiral because there are lots of planes of symmetry for both of these coordination compounds. We also introduced FAC and MER as geometric isomers if you have the case where you have a metal and 3 monodentate ligands of one type and 3 of another type. So this is another type of geometric isomer. And again, we do not have any enantiomers because both of these have planes of symmetry. So there are no optical isomers possible for either of these. Okay, so now we need to move forward and talk about chelating ligands. So chelating ligands are ligands that bind in more than one spot or have at least 2 or more atoms that are donating to our metal center. So something that's really important to understand about bidentate or multidentate ligands is that they decrease the overall symmetry in a complex ion or a coordination compound. So some common bidentate ligands that we'll talk about are ACAC or acetylacetonato, ethylene diamine, which we've already seen a lot, oxalato, and glycinato. So these are just a few bidentate ligands that you will see in this class. Okay, so I thought I would go ahead and do an example of determining the geometric isomers for a coordination compound that includes bidentate ligands. So we're going to figure out how many geometric isomers exist and also how many of those geometric isomers are chiral. So to do that, we need to go ahead and draw these structures. We have two options. We could either put, again, our chloroligands trans to one another, or we could put our chloroligands cis to one another. So here our ethylene diamine are also trans, And here our ethylene diamine are cis. So we have both our trans and our cis geometric isomers. So we have two geometric isomers. So the other thing we need to look at are either of these chiral. So again, to figure out if something is chiral, we want to look for a plane of symmetry. So if there is a plane of symmetry, then it will be achiral. If there's no plane of symmetry, then it will be chiral. So you can probably pretty easily see that there is a plane of symmetry that cuts right through if you cut right through these chloroligands on this trans isomer, you can see that this molecule is symmetric. So this is symmetric. So we're going to say that this molecule is achiral, meaning that no enantiomers exist for the trans isomer. If we come over to the cis geometric isomer, it might not be as obvious. So we talked earlier about how bidentate ligands decrease the overall symmetry of the molecule. So if you can't easily see it, what you can do is you can draw the mirror image. So let's go ahead and draw the mirror image for this, for this geometric isomer. So here's our mirror image. And so if we were to rotate this 180 degrees, then what we would get, I'll draw it right here. This nitrogen that's out in front is going to, if we rotate this 180 degrees, is going to move to this back spot. So we'll put that this nitrogen is back here. This nitrogen is going to move to this front spot. So that part matches up so far to what we have over here. But then we need to look at the other side. So the chlorine's going to say the same up top. And we have our NH2. Gosh, why does that keep happening? Okay, so this one out here in the front is going to end up right here. So we're going to put this nitrogen back here, and then our chloroligand will be out front right here. So now this bidentate ligand is coming back like that. So what we can see is that these two are not equal to one another. These two molecules are unique, and therefore this is a pair of enantiomers. Enantiomers. There are two geometric isomers, but we also have one geometric isomer that is chiral. So we have a total of 3 stereoisomers for this cobalt complex. Okay, moving on to coordination number 4. So with coordination number 4, we can either have square planar or tetrahedral, and we'll talk more about how to predict whether or not a molecule is going to be square planar or tetrahedral. But platinum-2 often forms a square planar geometry with a coordination number of 4. And if you have a square planar geometry and you have a metal with 2 monodentate ligands if you have a square planar geometry and you have a formula that's Ma2B2 with two different monodentate ligands, you will have two geometric isomers. You can have your cis or your trans geometric isomer. And I already mentioned this with cisplatin. This is cisplatinum. The formal name of this would be diamine dichloroplatinum 2. But these two molecules are different isomers. They have different properties, are cisplatin and are transplatin. But there are no enantiomers ever for our square planar geometry unless we have asymmetric ligands, which will not typically be the case in this particular class. In other classes you might see that, but in this class, most of the ligands that we use are going to be symmetric. Okay, we could also have a coordination number 4 that's tetrahedral. And if we had a formula that was a metal with 4 different ligands, such as nickel with a carbonyl, cyano, aqua, and amine ligand, we would not have any geometric isomers. So tetrahedral coordination spheres aren't ever going to have geometric isomers, but they will have enantiomers if you have 4 unique ligands. Okay, just to finish up isomers of coordination compounds, we can also have structural isomers of coordination compounds. The 3 main types are linkage, coordination, and ionization isomers. Linkage isomers happen when we have ambidentate ligands. So remember, ambidentate ligands are ligands that can donate from 2 different atoms. So thiocyanato was an example of a ambidentate ligand. We could donate from either the sulfur or the nitrogen. Nitrito is another example. It has the formula with a lone pair on the nitrogen and then also lone pairs on these oxygens. So you could donate from either the oxygen or the nitrogen. And we talked about with hard, soft, acid, base theory that sometimes how these ligands bind to the metal is based on if the metal is soft or hard. We also talked about thiosulfato that binds to silver. And again, this could have a linkage isomer if it was bound with the oxygen rather than the sulfur, but sometimes a metal will prefer a soft interaction. But this example over here with cobalt, both the nitrogen and the oxygen are both hard. So you'll often have these 2 linkage isomers where it could bind from either the oxygen or the nitrogen. So again, linkage isomer happens with ambidentate ligands that can coordinate in different ways or just essentially link to the metal in different ways. We can also have ionization isomers, and we've talked a lot about the difference between a negatively charged species if it's a ligand or a counter ion. So if you have an exchange between a ligand and a counter ion, then these are called ionization isomers. So here you can see this bromo ligand has swapped places with this chloride counter ion to become a chloroligand and a bromide counter ion. So essentially a ligand exchanged places with an anion or a neutral molecule that was originally outside the coordination complex. You can also have coordination isomers. So in coordination isomers, essentially ligands are exchanged with ligands in a different coordination sphere. So here you can see that the amines and the chloroligands switch spots. So that now over here, the amine ligands are bound to the copper and the chloroligands are bound to zinc. So those are the 3 types of structural isomers that you'll typically see. Okay, so just in conclusion, isomers have the same formula or the same composition, but very different properties depending upon whether they're geometric isomers or structural isomers. They can have very big differences in properties.